When you think about making something happen in chemistry, like cooking food or making plastic, what usually comes to mind? You probably think of heat, like boiling water, or light, like sunlight helping plants grow. But did you know that you can also start chemical reactions just by using force, like crushing, grinding, or pulling? This special approach is called mechanochemistry. It means using mechanical energy, physical force, to drive chemical changes. No heat, no light, no special chemicals. Surprised? Let's see how it works. Imagine you have two pieces of chalk. If you slowly rub them together, they just make dust. But if you press and grind them hard enough, you are actually changing how the tiny particles inside interact, sometimes even creating new chemical bonds. This is a simple way to imagine mechanochemistry in action. A classic example is using a ball mill, which is like a big container filled with heavy balls. When you put powder inside and shake it, the balls smash and grind the powder over and over. You might ask, why would anyone do that instead of just heating it up? Good question. Some reactions that need very high heat or toxic solvents can happen much more easily and cleanly with mechanical energy. For instance, scientists have made important materials called metal organic frameworks used to store gases or filter pollutants simply by grinding metal salts with organic molecules. No big ovens or harmful chemicals needed. Another exciting example is in polymers. Some special plastic-like materials can actually change their structure when you stretch or pull them. Imagine pulling a rubber band, and as you pull, some of its tiny building blocks rearrange into a new shape, or even repair themselves. This idea is used to design self-healing materials, like coatings that fix scratches automatically when stressed. You might wonder, how can force alone make molecules change? When you push or pull hard enough, you distort the chemical bonds inside the molecules. Think of it like bending a metal wire repeatedly. At some point, it breaks. In molecules, the bonds get stretched or squeezed until they snap or shift into a new arrangement. Another important point, mechanochemistry is considered a green chemistry approach. Why? Because it can avoid using toxic solvents and high temperatures, which saves energy and reduces pollution. This makes it more environmentally friendly and sometimes cheaper. So, is mechanochemistry only useful in the lab? No, it has real-world uses in making medicines, creating new materials for batteries, and even processing minerals. Industries are interested in it because it can help make manufacturing more sustainable and efficient. In short, mechanochemistry shows us that chemistry is not just about heat or light. It can also be about force. By simply grinding, pressing, or stretching, we can unlock new ways to make materials and drive chemical reactions. Mechanochemistry refers to chemical reactions initiated or accelerated by mechanical force rather than traditional energy sources like heat or light. Unlike thermal or photochemical methods, mechanochemical processes use mechanical energy inputs such as grinding, compression, or shear. This field expands the boundaries of reaction conditions by enabling transformations at ambient temperatures and pressures. Mechanochemistry can reduce energy consumption, avoid solvent use, and enable unique reaction pathways not accessible thermally. The approach offers an environmentally friendly and energy-efficient route to molecular synthesis. Ball milling is widely used to induce solid-state reactions between reactants without any heating. Like shaping metal by hammering rather than melting it, mechanochemistry uses force instead of heat to drive changes. Tribology traditionally focuses on friction, wear, and lubrication between surfaces, often leading to physical rather than chemical changes. In mechanochemistry beyond tribology, mechanical stress directly drives chemical bond breakage and formation within molecules. This field involves bulk, or localized mechanical activation, such as through ultrasonic waves, high-pressure shear, or tensile stretching. Unlike surface wear or deformation in tribology, mechanochemical reactions yield new chemical products and alter molecular structures. The distinction emphasizes a transition from mechanical effects on materials to using force as a precise chemical activation tool. Ultrasonic cavitation can fragment polymer chains and create reactive species, leading to new polymer architectures, like using a blender to mix ingredients into a new sauce rather than simply stirring them. Mechanical energy can selectively activate specific chemical bonds by deforming molecules beyond their elastic limits. Under stress, energy is concentrated in certain regions, facilitating bond cleavage or rearrangements. This localized energy input allows reactions to proceed under mild overall conditions, avoiding the need for global heating. Mechanical bond activation can be highly selective, enabling transformations that are challenging or impossible under thermal conditions. These unique pathways open opportunities for designing new synthetic strategies and responsive materials. Applying tensile force to certain polymers can trigger chain scission and induce fluorescence in mechanochromic materials. Like bending a glow stick until it snaps and starts glowing, mechanical force activates a hidden chemical response. MechanoChemistry aligns closely with green chemistry principles by minimizing or eliminating solvent use. Many mechanochemical reactions proceed efficiently in the solid state, reducing hazardous waste and environmental impact. The elimination of solvents simplifies product purification and reduces energy required for solvent recovery. Additionally, mechanochemical methods can decrease reaction times and improve atom economy. These advantages make mechanochemistry an attractive alternative for sustainable synthesis and industrial applications. Solid-state synthesis of metal-organic frameworks via ball milling avoids toxic organic solvents traditionally required, like making bread by kneading dough directly rather than dissolving ingredients in water first. Several specialized techniques enable mechanochemical activation, including ball milling, twin-screw extrusion, and ultrasonic treatment. Ball mills generate impact and shear forces through grinding media collisions, while extruders provide continuous scalable mechanical stress. Ultrasonic devices induce cavitation bubbles that collapse violently, producing local high-pressure zones. Each method offers control over force intensity, duration, and distribution, allowing fine-tuning of reaction outcomes. The development of precise mechanochemical instrumentation has expanded access to diverse chemical transformations. Twin-screw extrusion enables continuous production of pharmaceutical core crystals without heating, like using different kitchen appliances, mixer, grinder, blender, to achieve specific culinary textures and reactions. Mechanochemistry can enable reaction pathways distinct from those accessible via thermal or photochemical activation. Stress-induced intermediates may bypass high-energy barriers, leading to novel products or enhanced selectivity. For example, certain metal-catalyzed couplings or solid-state organometallic reactions only proceed efficiently under mechanical activation. These alternative pathways broaden the synthetic toolbox and enable the design of materials with unique properties. Exploring these non-traditional routes fosters innovation in molecular synthesis and material science. Direct mechanochemical synthesis of complex pharmaceutical intermediates without traditional solvents or high temperatures, like forging a new hiking shortcut over a mountain instead of following an established winding road. Mechanophores are molecular units that change structure or function in response to mechanical force. Incorporating mechanophores into polymers or materials creates systems that visually or functionally respond to stress. Such materials can self-report damage, change color, or release active agents upon mechanical activation. These smart materials have applications in sensing, self-healing, and adaptive technologies. The design of mechanophores relies on understanding precise mechanochemical activation mechanisms at the molecular level. Stress-activated color changes in polymer coatings indicate material fatigue before catastrophic failure. Like bruises forming on skin to signal internal damage, mechanophores visually reveal mechanical stress in materials. Controlling mechanochemical reactions presents unique challenges, such as reproducibility and precise energy input quantification. The heterogeneous nature of mechanical force distribution can lead to variability in product distributions. Researchers are developing strategies like in situ monitoring, advanced milling control, and computational modeling to improve predictability. Understanding the interplay between mechanical energy, material properties, and reaction kinetics is critical for advancing the field. Addressing these challenges will enable more widespread and reliable application of mechanochemistry. In situ Raman spectroscopy during ball milling helps track reaction progress and optimize conditions, like adjusting the heat and stirring speed while cooking to avoid burning or uneven mixing. Mechanochemistry holds promise for revolutionizing chemical synthesis across pharmaceuticals, material science, and catalysis. Future advances may enable the design of energy-efficient, solvent-free manufacturing processes on an industrial scale. Combining mechanochemistry with automation and real-time analytics could lead to smart adaptive synthesis platforms. Additionally, expanding mechanochemical principles to biological and hybrid systems may unlock novel therapeutic and biomaterials innovations. This paradigm shift represents a move towards more sustainable, versatile, and innovative approaches to chemical transformations. Emerging research explores using mechanical forces to activate catalysts directly in living tissues for localized drug release. Like creating electricity by pedaling a bicycle rather than plugging into a grid, mechanochemistry offers an alternative, direct energy route to drive chemical change.